Okay, we're going to do a lo-fi video for simplicity's sake about the molar mass of a gas slab and how we calculate the uncertainty. So if you're going to calculate the final uncertainty on the molar mass of gas, you got to think about where that calculated value came from and which measurements you used along the way. Every time you use a measurement, you have to include its uncertainty. So remember that the overall equation is molar mass equals mass divided by moles. So we've got to eventually figure out what's the percentage uncertainty on the mass of gas and what's the percent uncertainty on the moles of gas. And if we add those together, we'll get the total percentage uncertainty, which we can convert into absolute uncertainty following our normal uncertainty rules. Let's take that one piece at a time. Getting the moles of gas was a lot simpler than getting the mass of gas, so let's start there. The moles of gas uncertainty is going to be based on the measurements that got us the calculated value for the moles of gas. If you remember, we got the moles of gas by using the ideal gas law, pressure times volume divided by ideal gas law constant times temperature in Kelvin. So all three of those values, pressure, volume, and temperature, those are all experimental values that we measured directly in the lab, and all of those have uncertainty. If you can convert all of those uncertainties into percentages and add them together, you'll get the total percent uncertainty on the moles of a gas. So percent uncertainty on pressure, percent uncertainty on volume, and percent uncertainty on temp combined will give you the percent uncertainty on the moles. Okay. Remember, you took a lot of volume readings. So you're going to have to add those together first before you get the total percentage uncertainty on the volume. And when you do temperature, you should do the calculation in Kelvin, since that's the value that you're using in the ideal gas law. So these 3% uncertainties combined should give you the percent uncertainty on the moles of gas. So that's the moles one taken care of. We're all set there. But now we've got to do the one for mass, and mass gets a lot more complicated. To kind of walk through it, you really need to think about the total steps that you did for the calculation of the mass of gas. To get the mass of gas, you took the mass of the bottle and gas, something you measured directly, so you actually have a little plus or minus grams on that value. And you subtracted out the mass of the bottle, but the mass of the bottle was something you had to calculate. So I'm going to break that down further. You calculated the mass of the bottle by doing the mass of bottle and air minus the mass of air. And this one, the mass of the bottle and air, that was another thing that you measured. That was the first thing that you measured. But the mass of air was something you calculated. So again, let's break it down further. The mass of air came from calculating the moles of air times the molar mass of air. Now, if we assume that average molar mass of air was about 28.96 grams per mole, let's just be nice to ourselves and say that has no uncertainty, or at least negligible uncertainty, so we can pretend like it has no uncertainty at all. The moles of air, though, does have uncertainty. Thankfully, you've already figured it out. The percentage uncertainty on the moles of gas is actually also the percentage uncertainty on the moles of air, because it came from the exact same calculation. So our percentage uncertainty here is what we're going to end up having to use. There's a couple of ways you could approach these final steps. Here's how I think is the simplest way to do it. You've got a percentage uncertainty on the moles, and since there's no uncertainty on the molar mass, this percentage uncertainty on the moles is going to really be the same as the percentage uncertainty on the mass of air. This is not contributing any uncertainty. This one's giving you all the uncertainty for this calculated value here. So you've got a percentage uncertainty on the mass of air, and just to make things simpler, you can convert that into a plus or minus grams on that mass of air. How do you do that? Well, let's say we have 1% uncertainty on the mass of air, and let's say the mass of air is 1 gram, just to make it nice and simple. What's 1% of 1 gram? It would be plus or minus 0.01 grams. So just like you would do a percentage into a regular uncertainty before, make it a decimal, 0.01, times the actual mass, and you get the uncertainty as an absolute uncertainty. So let me try to explain this as clearly as possible, because it is a lot of steps. this uncertainty percentage of moles, which you previously figured out, you can use that. That's the same as the percent uncertainty on the mass of air, and you can convert that percentage uncertainty into an actual absolute uncertainty with grams. Once you have that, if you can get a plus or minus some gram amount on the mass of air, now you're actually doing simple subtraction. And so you're going to be able to combine these three mass uncertainties together to get the total uncertainty in grams on the mass of your gas. Okay? And from there, you can convert that value into a percent. And if you've got that, now you've got this value up here that we talked about before. You'll have the percentage uncertainty on the mass of gas. Combine these two values and you'll have the total percent. So it's a lot of steps. It's very complicated, but the calculations to get here were pretty complicated, so that's why the uncertainty calculations are tough. So get the mole uncertainty first as a percent. You will include it once for the uncertainty on the moles, but you'll have to use it again down here because we use that value again in our calculations, so the uncertainty affects us twice. And you'll have to get these mass uncertainties combined to get the total mass uncertainty. So try to follow these steps and see if you can come up with a total uncertainty on the molar mass value from your lab before we have class next time.